Hello, good morning. This is a continuation of our EASY lecture series, EASY modeling and simulation, realistic modeling and simulation of earthquakes, soils, structures, and their interaction. We had a short break while I was trying to get back to California from Switzerland. Took some driving and some flying on empty planes and so on. And then again, some driving. Together, we are back together in California. Today with me are again Dr. Han Yang.
Hello.
And Mr. Heshen Wang.
Hi.
And we're all three of us are in Davis, and we continue our lecture series. And this lecture will be about presentation of different types of models for reinforced concrete beams and shells and walls and plates. And this is going to be done by Han, Dr. Yang. And so Han, please share your screen. And so we can get going.
Okay.
Can you do it? Should I do something special?
Yeah,
okay.
I
Good.
think, yeah.
Good.
Can you see this? Yes.
Yep, I can see this.
All right. Full screen. Full screen. Okay. Okay, thank you, Professor Boris, and good morning from Davis in my apartment. First, I need to apologize. I think there's some leaf blowing going on outside my apartment, so if you hear any noise, just please ignore that. And with that, so I'm gonna start talking about elastic plastic material models for reinforced concrete beam column and shear or shell or a shear wall or a plate. So here is a brief outline of my lecture today. So first I'm going to talk about the finite element modeling of a reinforced concrete beam column and shell, wall, or plate. And then together with the finite elements, we have basically three different types of material models that we're going to use together to model reinforced concrete structural elements. So we have the uniaxial steel fiber material, we have the uniaxial concrete fiber material, and also the 2D version of the plane stress concrete damage material model that's going to be used for shell or shear wall elements. So I should mention that the finite element and material models shown here are mainly for pure bending and axial loading of a beam column or walls, plates, and shells, and that the influence of shear loading or shear deformation is not taken into account. Now, other researchers have developed other additional methods to mitigate the effect of shear deformation, but that is not considered here.
If I may just say, this is really important. All these fiber elements and all these elements that have a plane essentially stress for shell, wall, and plate really rely on just pure bending. And this is really important. If one wants to go to some influence of shear, of course you can go to Timoshenko beam, but in that case it's not nonlinear. What I've seen people mostly do is go to solids, use solids to model both beams and shells and plates and whatnot. So with that caveat, I mean, it's really important. This is for pure bending and axial loading, and this is rarely mentioned when you see results of this kind. Anyway, I'm sorry. Go ahead.
Yeah, sure, no problem. Okay, so now let's move on to the modeling. So I'm going to briefly talk about the modeling of reinforced concrete beam or column elements first. So the method here we're using is so-called fiber section technique. And the real easy DSL command here, the keyword here is the fiber section. So this method was developed by Stockholm and his colleagues in 1996. So the basic idea is to separate a cross-section of a beam column into different uniaxial fibers. As you can see, this plot is showing right here is a cross-section of this beam, of a reinforced concrete beam right here. So as you can see, after you divided the cross-section into different uniaxial fibers, you can define each fiber with different material models. On the outside layer, you can have unconfined concrete, and then as denoted by this red dot here, they are the steel rebars, and then inside you can have core confined concrete. Yes, please.
If I may say so, so the
Sure.
confined concrete is inside hoop reinforcement, and so that's
Yep.
the one that is confined, and this is much stronger concrete. The one that's outside is outside of this longitudinal and hoop reinforcement. More important is the actual hoop reinforcement,
The
and
hoop,
that's an
yes.
unconfined concrete, much weaker, but it's okay to model it, but it's gonna eventually flake off. Yes, go ahead.
Right. So then, to basically to model the steel material and the concrete material shown here, we have two different uniaxial material models. We have the uniaxial underscore steel O2, that is a keyword for the steel rebar material in Real Easy, and also we have the uniaxial concrete O2 material, that is for the concrete, both unconfined and confined. You can later define different material parameters to represent the confined or unconfined concrete part of the cross section. Similarly, we can use basically a very similar approach for shell or wall or plate elements. The main difference here is that instead of a cross section with uniaxial material, now we have a plane stress layered material, because now it's going to be a wall, so it's going to be a 2D material basically. But it's still going to be separated into layers, and then each layer is going to represent a different material, and then when you combine them together, they can be used to simulate the behavior of a purely bending or axially loaded shear wall or shell or plate. So here the finite element formulation we are using is so-called shell NLDKGQ. This element formulation was developed by Professor Lu from Tsinghua University in 2015. And coming together is the plane stress layered material that is used to combine all the different layers of material that I'm showing right here. You can have on the outside, on the cover, you can have an unconfined concrete layer, and then you can have rebars. Note that the rebars can be in different directions. Here I'm showing you can have 2 layers of X direction sphere rebars, and then you have Y direction, and even if you have the rebars that is not vertical or horizontal, you can also have them. You just need to define an angle which they exist, then it can also work. So then here for the concrete material, we have the 2D version of the concrete damage material model. Here is the DSL keyword for that. This model was originally developed by Professor Faria and his colleagues in 1998. When it was developed, it was actually a 3D concrete damage model, but here we are using the plane stress version, the 2D version of the material model. And then again, we have the same uniaxial steel material model to simulate the rebars. And then when you have the uniaxial and then you give it a direction, then later you can combine them together so that the element knows what the direction of the rebar is. Later we will show more examples to better explain and represent this kind of modeling technique.
So if I may just quickly add, so this is really just a
Sure.
bunch of layers of concrete, confined, unconfined, and then layers of rebars at different orientations. And then for pure bending and for axial loading, for pure bending it's for plates, for axial loading for walls, and then combination of bending and axial loading is for shells. You can essentially model a shell in general, and subset of a shell is a wall, and the subset of a shell again is a plate bending as well. So yes, go ahead.
Right. Okay, so next I'm going to briefly talk about each of these 3 material models, how they work and what kind of material behavior they can represent. So here the first one is the uniaxial steel material model. As I mentioned before, this is the uniaxial steel O2 material inside the Real Easy. So this material model was developed by Neto and Pinto in 1973 and later extended by Professor Filippo and his colleagues in 1983. So this is the current version of the model we are using inside the code. So it can capture the nonlinear hysteretic behavior and also the isotropic strain hardening effect of the steel. Here are the main governing equations for the material model. Obviously, there's tons of more formulations, but I'm not going to go into detail here. If you're interested, you can always go into our menu for Real Easy, which is available online. At the end of the presentation, I will show you the website, so you can go there and check it out for yourselves. So the main parameters here are the current stress and strain. Note that the material is uniaxial, so you have a scalar stress and scalar strain. And also you have the stress and strain at the point of strain reversal. These two parameters are served as material internal variables. Basically, it remembers the loading history, the loading path of the material. And also we have a number of material constants to define a more detailed stress behavior and also the hysteretic behavior of the model. Next,
I'm sorry. Go back one slide.
Sure, yeah.
So just to clear. So this is exactly the same material model that's in OpenSeas. We got this one from OpenSeas. This is, and the name is the same just because we just wanted to make sure that people know this is exactly the same from OpenSeas. So if you have calibration from OpenSeas for uniaxial steel 02, and you'll see for concrete, it's going to be essentially the same. It's the same material that was developed by Menegotto and Pinto, and then extended by Professor Filippo, and used later on by Professor Spaccone, and so on and so on. So yes, go ahead.
Yes, that's right. And similarly, the same situation for the uniaxial concrete O2 material. Again, it comes from OpenSea. So again, so if you have that calibrated, then you can directly use it as well. So this material model was developed by Yassin in 1994 in his, I think, PhD thesis, if I'm not mistaken.
I think so, yeah.
So, yeah, right. So the nonlinear hysteretic behavior and damage effects in concrete are both considered in this material model. So here, first, if we look at the monotonic behavior, specifically the monotonic compressive behavior here, it is separated basically into three regions. Before you reach the peak stress here, you have a branch that is mainly elastic, but there are definitely some nonlinearity going on here. And then once you reach the peak stress and you start to rapidly have a decay, then there's another region of your behavior. And when you reach the ultimate strength, the model assumes that you have a constant ultimate strength going on later when you apply even more strains. But you can always, for unconfined concrete, you can always put this parameter to be 0, so that you have 0 ultimate strength, which is indicated by most experiments. So here again, the main material parameters are the current stress and strain. Again, it's uniaxial, so those are scalars. And then you have a number of first, you have a number of physical material properties that can be directly determined from experiments or tests, or from literature if you have similar materials. And then also we have a number of more detailed material properties to kind of fine-tune your material model behavior. So for the cyclic behavior, it is mainly defined by this parameter lambda. Here, it assumes that all reloading lines intersect at a common point. So as indicated in this plot right here, no matter where you unload from this compressive envelope, you're assumed to come back to the same common point, which is defined by this epsilon r and sigma r here. So the unloading response is bounded by those two limits. So those are kind of more detailed formulation for the model itself. Here we have the sigma m and epsilon m. So those are the stress and strains at the unloading point on the compressive monotonic envelope. So again, those two are served as material internal variables to kind of account for the stress loading history.
Okay.
Yeah. So next, the third material model we have is the 2D version of the concrete, the plastic damage model that is used for shear wall, a plate, and shells. So the keyword here is used in real easy is the plastic damage concrete plane stress here. So this is the 2D version, the plane stress version of the plastic damage model developed by Professor Faria and his colleagues in 1998, as mentioned before. So main features of this model is that it has distinct stress-strain envelopes obtained under compression or under tension. In other words, the evolution of the tensile behavior and compressive behavior are separated. So like when you have plastic damage in the compressive side, it does not have effect like influence on the tensile side. So they evolve separately. And also we have stiffness recovery after the loading reversal. We have a higher concrete strength under 2D or 3D compression test compared to 1D loading. And also the plastic deformation is discernible after some compressive stress limit is reached. So all of those behaviors comes from the test and physical experiments. So this model is capable of simulating all of those behaviors. So which is one of the main reasons we use it for simulating the behaviors of concrete shear walls and plates. So later, yes.
Just to show, so this is really good model. It's actually based, one of the rare models that's actually for concrete that's based on thermodynamics, and it's a full 3D model. This is a version in 2D in plane stress, but it's a really, really good model. Go ahead.
Right. So later, I will when we continue on our lecture, we will show more examples and detailed, real easy DSL commands for all those material models, and also some examples to explain and illustrate how can you define those material parameters and what are the influence if you change some of them. So this is the introduction part, and here are the references if you're interested in more detailed theoretical or computational formulation. And here are the collaborators, Mr. Hesham Wang here and Dr. Yuan Feng. And also I would like to thank the fundings and collaboration from the funding agencies. And again, for more information, please go to our Real Easy website for our menu and more examples and explanations. Thank you.
Thank you very much. So if you will stop your screen sharing.
Yep.
Just good. So thank you very much. We'll continue with next set of lectures, but at the moment I'll stop recording.